Okay, welcome everyone to quantum topology. Quantum topology. Who doesn't like quantum topology? So the topology part of quantum topology, or whatever I call topology, is actually over. Oh, it's too bad. It's too bad. It's too bad. And now we do, additive categories. What is an additive category? Well, let's have a look at the following. My favorite topic of all time. So let's see. Linear algebra. Beautiful. Linear algebra. Let's do AI mode. AI mode is always fun. Linear algebra. Blah, blah, blah. Vectors and stuff. Essentially, linear transformations, vector spaces, vectors, matrices. Nah, this is already... Linear algebra is really about solving linear equations. That's what it is, right? Here, intersections of planes or something. That's really solving linear equations. And it's literally the best thing since sliced bread. So it's pretty new. Let's see. It spans over 4,000 years. But the birth of the determinant, and then vectors are pretty new actually. So maybe 18th century, and maybe really roughly around here, right? Of course, people solved linear equations a long time ago. Yeah, mathematicians haven't invented linear equations. Linear equations just were solved. It's just solving linear equations is just part of human history. It's not something mathematicians came up. Mathematicians came up with methods to solve more difficult equations and then realized that they can't do it. And it turns out that linear algebra is literally the only thing we ever can do. Very, very sad. So it's very, very sad. Yeah. So let me repeat, because it's a bit sad. Linear algebra, solving linear equations. So here AI was a little bit lying to you. Yeah, sure. Linear algebra is about vectors and matrices. But it's really about solving linear equations. Is the only thing that really works. It's very sad. As soon as you try to solve anything else, you're just dead. You of course can solve special cases of other equations, but a really good kind of very clean linear algebra style study of higher equations, whatever that means, just doesn't exist. And that's why it's kind of interesting, right? So linear algebra, part of human history essentially, solving linear equations, works really well, and that's why a lot of other mathematics, a lot of other of the sciences are kind of modeled after linear algebra. So I'm not saying life is linear algebra. I'm saying humans interpret life to be linear algebra because linear algebra works so well. Linear algebra is therefore one of the most applied things you will ever find ever. And it's just so good. So essentially the idea is everything we have done so far is too complicated. So let's forget it. Let's just map it into linear algebra and see what linear algebra can do for us. Along the way, you should expect to lose some information, and we will talk about that way later. So it's not like a one-to-one mapping, but you're in linear algebra now. So you have some linear equations you can solve, and linear equations make everyone happy or sad, I don't know. But linear equations are at least solvable, in contrast to literally any other equation you will ever see in your life outside of special cases. That was actually wrong in some sense, because turns out it's kind of the same effect, right? People model the world after linear algebra. It's not linear algebra. It's modeled after linear algebra because linear algebra is so powerful. And of course, the equations, the nonlinear equations you see in your life, are also somehow most of the time not too bad, because what people throw at students are the solvable special equations, right? So whenever you have an integral and you need to integrate something, it usually works. But if you take a random integral, there's no way you integrate that. Anyway, so what you ever see in life is pretty random, but what people make out of it, and in the end what you have to do in your own life, is very often some form of a special case of a special case, which is actually solvable. And very often this special case of a special case is just a linear equation where you can use linear algebra. And this is kind of a general thing life does, very general. And we're trying to apply the same concept in quantum topology, right? Quantum topology, too difficult. Let's send it into linear algebra and see what comes out. Okay, that was a long ramble at the beginning. Let's just have a look. Linear algebra. Oh, linear algebra is so good. So I have a whole series on linear algebra that you don't need to watch, but it's literally the art of solving equations, right? So the picture we just saw, here's it again. what is an intersection of three planes? Well, that's solving a linear equation, and as you put in the matrix, whatever. And linear algebra is your machine to actually do that. Right? And kind of the point is, and a little bit of repetition, of course, now, the braiding, etc. So what we did so far, braided categories, ribbon categories, pivotal categories, was pretty good, was fun. It gives us a way to read diagrams, but we still can't do anything really with it. Right, so invariants should be kind of computable, so we want some number thing, and as I said, the only thing we actually know how to compute is linear algebra, so send it into linear algebra. I will make it a bit fancier. I will call it the categorical version of linear algebra, so additive categories or abelian categories. But it's really just linear algebra in the end. It's just something people usually like to do a lot. So you put in something that looks like a huge generalization. It's actually just a tiny generalization, but the language kind of blows up a little bit and it looks much more complicated. Very exciting, very good strategy to get your papers published in good journals. Yeah? You just blow up the language, you have one extra case that you can solve, and it looks very, very, very convincing. So really, it will sound a bit strange when we go on, but we're really just doing linear algebra, and we really just find a different language to express our ideas of linear algebra. And essentially what we do is, the first thing you notice is the kind of very basic fact. Between two vector spaces, the maps themselves, so the matrices, form a vector space, which really just means you can multiply matrices. That's kind of the categorical structure, but you can also add them or scalar multiply them. Yeah. So between kind of the structure repeats itself. Between vector spaces, you have vector spaces. And that's essentially what we need for an additive category. We just say our category is additive when it's kind of modeled when we can add morphisms essentially. So we can add pictures in the end. Yeah. So we can subtract whatever with a zero map. And an additive category is literally just that. Yeah. I give you some more details, but not right now. This is kind of the flavor is additive categories is what you need to do to have a linear algebra in categories. That's literally what we do. Okay. And you will see things like this. So it looks very fancy. So we have a direct sum, which literally is just, you take a matrix here, and you take a matrix here, and you put them in this nice block form. That's a direct sum. And you do that categorically, maybe more like that. So a direct sum is kind of the unique object, x plus y, with an x here, y here, with projections and inclusions satisfying, well, they are the identity. If you go like this, they're the identity on y. This is this one. When you go like this, they're the identity on x. And the interesting one is the splitting here. So if you do it the other way, this plus that is the identity on x plus y. And this essentially uniquely determines what the direct sum is, but in reality it's just that. So that's what I mean by using categorical language to describe a linear algebra phenomenon, right? So this is like block decomposition of matrices in terms of categories. Yeah. So zero object, you can also define that in this framework. There's nothing. A direct sum is that thing, and whatever projections and MOOC equations, projections and inclusion type things. We'll make that more precise as we go along. But essentially, that's the idea. We take linear algebra operations like that one. Matrices already do that, of course. The direct sum of matrices is literally this nice block matrix thing, right? No interaction between this part and that part. And I can zoom out a little bit. Beautiful. Oh, look at that. Oh, beautiful. And it's just modeled along that, and you just find a categorical language to express it. So direct sum is this operation we want, and it literally just means we can have block matrices. And we have some enrichment in vector spaces, which literally means we can add things. So essentially, it's like a matrix model of categories, an additive category. Next time, we'll have a good definition, but this is just what it's supposed to be. Yeah. So, as I said here, the abstract definition is only packaged what matrices have done anyway. And turns out if you really push that any further, if you go to abelian or something, I will be back to vector spaces anyway. So it's a bit, as I said, it's a bit, I mean, you still get a little bit more, of course. So you have nicer and cleaner language. That's pretty good. But in the end, language is also sometimes scary. It's just matrices again. And the universal property mindset is essentially you define something by some diagram in the categorical sense here, yeah, and something by universal property. Why would you do that? Because it buys you this fabulous uniqueness up to unique isomorphism, so it's as canonical as it gets. So there's not really a choice involved, right? That's the whole point. We often determine objects by what they do. Yeah? Direct sum is like the decomposition into two parts that you can split off, for example. So that's not how they are built. And this is kind of this idea of universal property, right? So you define something by what they do. We will zoom into this picture as we go along. But that's kind of the idea. Let me say that again. So we are going to, you want linear algebra because linear algebra is fabulous. We want to map our topology into linear algebra. Yeah, linear algebra, fabulous. Thumbs up, 10 out of 10. Linear algebra. And in order to do that, we kind of want the correct categorical language for linear algebra. So we take what matrices can do anyway and kind of find this universal, this type of thing, the what they can do type of description of things, and define things like additive categories, abelian categories, and finite abelian categories. We'll see quite a few of them. Anyway, I hope you enjoyed this video, which is kind of a teaser. Teaser is a correct word. Oh my goodness, that took me a long time. The teaser for what is going to come in the future. Anyway, I hope you enjoyed this video, and I also hope to see you next time.